And from this slide. But before we start, oh yeah, I meant to call roll first. Sorry, I don't like to have a roll on the recording. Walter's not here yet. Gavin's not here yet. Dawson is. Happy October, everybody. I just put you in the wrong place. Yeah, in the right place. Here. Okay. Andrea's here. Josh is here. Jake's not here yet. Allison's here. And Chris and Jalen aren't here yet. So 4 here. Okay. The announcements I know about. I saw posted on the board. I bet you I've got one in my email, but I haven't seen it. There is a special presentation of Broadway hits coming up Friday on the Birmingham East Campus. That's in the A.G. Gaston Auditorium, and it's a UAB touring company that's doing it. And I bet you it's going to be quite good. And I wouldn't be surprised if there may not be an Austin student or two in the UAB course. I don't know that there is, but I know that we have a pretty tight relationship, so I wouldn't be surprised if you might not see one of our graduates there. But it should be quite a good thing. I believe it's 9 or 9:30 in the morning on the East Campus. So check out the flyers posted on the wall. Check those out. Should be quite good. All right. We talked about applying for graduation. I don't think any of you are graduating this term, but if you just remind yourself, the term before you graduate, that's when you start your application process. That way you discover everything you need and can get registered for what you do need, identify those problems that might be coming up, and get those taken care of as well. Now, the Office of Student Services is seeking students who are interested in becoming note takers. We have certain students who have some type of challenges that they can't take notes for themselves, so they will pay you to take notes. So please consider doing so. And the Space Center was looking for peer tutors. I don't know if this is both campuses, but I know it's on the Birmingham campus. They were looking for math, English, biology, computer science, and Spanish on the Birmingham campus. They probably are looking here too. Check it out. We also have tutoring down the hall here at Student Support Services. I don't think they have that on the Birmingham campus, so check out that. They will pay you to tutor. So check those out. You can help another student, improve your own abilities, and on top of it all, get paid. Okay, Chris is here. All right. Yes, second. Walter, I'm sorry. I've done that twice today now. I'm marking the wrong person. Okay. Let's try to get those. All right. All right. Any questions on anything we've done so far? Okay. Just as a side note here, I've only received 2 of the first test in. Only 2. So please, folks, let's be getting those in because we're coming relatively close to finishing the material for the second test, and it's really a good idea to have the first one in before you get the second one, because there may have been something you're missing on the first one, and if you turn it in the same day or after you get the second test, you're not going to see your error on the first one and make them all again on the second one. So don't do that. Get them in sooner rather than later. And research papers, let's see. Oh, only 1 of those in, so please, folks, get those in too. All right. No questions? All right. Last time we were just introducing inverse trigonometric functions, and we gave the things. We looked at the graphs. Remember that they had to be 1-to-1. And here is the statement that follows the graph. Here's the graph we were talking about. This is for the sine function. Only has an inverse on that interval from minus pi halves to pi halves. However, when you restrict the domain to the interval minus pi halves to pi halves for x, that corresponds to the right portion we just solved, the following properties hold. On that interval, from minus pi halves to pi halves, including the endpoint, the function y is equal to sine x is increasing, strictly increasing. Remember, one-to-one functions are either strictly increasing or strictly decreasing. Okay? Now, on the interval, minus pi halves to pi halves, y is equal to sine x, takes on the full range of values, from minus 1 to plus 1. Those are the only values it ever takes. It gets them all. Okay? And then third, on the interval from minus pi halves to pi halves, sine y is equal to sine x is 1 to 1. That's why we chose it, because it was 1 to 1. So these three issues here all have to be met for you to deal with one-to-one functions. Well, deal with invertible functions. They have to be one-to-one, take on the full range of values, and either strictly increasing or strictly decreasing. That's part of being one-to-one. All right, any questions? So, on that restricted interval, minus pi halves to pi halves, y is equal to sine x has a unique inverse function called the inverse sine function. Now we have two designations for this. This to me is the older one, but the book seems to really like it. This to me is a lot more current. It's more in keeping with the other. Now there may be a reason they don't like that one as much. I think I might know what it is. The arc sine, and that almost comes from the association of a central angle with its intercept at arc length of a unit circle. Yeah, that helps me remember that. The arc, it has to do with the arc of the unit circle, okay? The associations there. So the arc sine, or I prefer, because it's easier to write, inverse sine, okay? And we talk about all other functions as inverse functions, okay? This is Jalen. All right. So the only little drawback here was the same one you had for any inverse function. That doesn't mean 1 over sine. Okay? That's not what, if it was x to the minus 1, that means reciprocal of x. If it's 7 to the minus 1, that means 1 over 7. Okay? Sine to the minus 1 does not mean 1 over sine. Okay? So that may be the reason they usually go with this more than that, but that's true for every inverse function. Notation, inverse sine of x, consistent with inverse function of x. Okay? The arc sine notation comes, I think, from, well, it says it comes from that association. Fine. Okay. So the arc sine of x means the angle or the arc whose sine is x. So that's what that means. Well, that's exactly what inverse sine means too. And let me just write this. This implies, let me get my pen set up. Okay, this implies, can someone give me an equivalent equation to this one using the same everything except the minus 1? An equivalent equation. It has x in it, it has y in it, it has sine in it. What's exactly equivalent to that? Not quite. X equal sine y. Okay? That is, if you see y is equal to inverse sine of x, that implies that x is equal to sine of y. Because you take the sine of both sides, that becomes sine y, and sine of sine inverse, that just gives you x. Okay? So that's exactly equivalent equation there. And you can do that with every inverse function. Just flip the function and flip the variables, basically. And that's also what this means. Just like they say here, arc sine means is the angle or arc whose sine is x. Okay? Now, here's the other way I think of it. I don't know if this is helpful to you or not, but it helps me remember. When you're doing y is equal to sine x, okay? Now, I know the book likes to call that x any real number, some real number, you know, and it's true, any real number. But I like to think of that as x is an angle, right? Represents an angle, okay? And the y represents a value that's associated with the angle, okay? So the x is the angle, the y is the thing. So when you have y is equal to the inverse sine, this is your angle, that's the number. You flip it, okay? So you're looking for the angle whose sine, the sine of this angle is equal to that number. So that's, I also think of it that way. The arc sine means the angle, or the arc, whose sine is x. The sine of that angle is equal to x. Okay. And therefore, when I do it, quite often I'm going to use Greek letters like theta to remind me this is the angle, that is the value. Okay. Both notations, arc sine and inverse sine, are commonly used in mathematics. So remember that the sine inverse sine of x denotes the inverse sine function, not 1 over x. If you want to write 1 over sine x, make that cosecant x, okay? Or 1 over sine x. But don't write it as inverse sine. That's a different meaning. Now, here's another issue here. Remember, arc sine, whatever this is, that's going to be the angle. This thing represents an angle because that's the number. Remember, the sine of an angle gives you a number, and arc sine of a number gives you an angle. Those angles are between plus or minus pi halves. And J's here. All right, good deal. Just missing 2 now. Hopefully they will be in. So here is the graph of the arc sine or inverse sine of x. Now, remember, I always think in terms of sine and later cosine. The sine of pi halves is going to be minus 1. So the inverse sine of minus 1 has to be minus pi halves. Sine of 0 is 0, so the inverse sine of 0 is 0. Sine of pi halves is 1, so and this is Chris, right? Okay. I marked you here once, okay. Mistakenly. Okay. Still missing Gavin. Okay. So, just keep in mind, the x here is a number, the inverse sine is an angle. So that's why the minus pi halves and pi halves make sense here. The value of x is going to be from minus 1 to 1. And sure enough, going from minus 1 to 1, this goes from minus pi halves to pi halves. Okay, just like the sine is an increasing function on this interval, so is the inverse sine an increasing function. Now, I also think of it this way. The sine function has a slope approaching 0 here, because that's where it's getting ready to turn up. It goes up here and approaching 0 here. So this has an infinite slope here and here, or approaching it anyway. Okay? So those are the 2 things. Now here's the other thing. This is almost a straight line right here. It is for sine and it is for inverse sine. So these are, that portion right there is almost always close to being identical. Not quite the same, but close to it. Okay, so some of the features of your inverse sine function. That's the only place it's defined. Don't define it over here or anywhere there. Okay? Now, remember this when you're doing later solving trig equations and things like this. Your only answer here is going to be an angle between minus pi halves and pi halves. Even though your problem may have something in the third quadrant, okay? It's not going to show up here, okay? And because you see, if you think about this, this is 4th quadrant, 1st quadrant. So the 2nd and the 3rd quadrant aren't represented on this graph at all. So later when you're actually solving things and you have an angle that's somewhere else, you're going to have to pull the angle here and relate it. We'll we'll get there later, so don't worry about that yet. That is an issue that will be arising. All right. So here's your definition of the inverse sine function. The inverse sine function is defined by y is equal to arc sine of x, or inverse sine of x, I prefer, if and only if sine of y is equal to x. So that's exactly what I was saying before on the last couple slides ago. This is exactly what the meaning is. If y is equal to inverse sine of x, that implies the sine of y is equal to x. Has to be. These are what I consider equivalent equations. Okay? So keep those in mind. Now, remember your x now is the numbers. Those have to be between -1 and 1. But now they're your horizontal axis. This is your domain now. The y is your angle. And that has to be between -pi halves and pi halves. Okay? Domain of this, that's the x values, is the range of this one. That's the x values here. The range is between -pi halves and pi halves. Because that's your angle. That's your number. That's the angle. That's the number. Same variable in this case. So remember, this now puts them as, this as the domain, that is the range. Over here, this would have been the domain, that's the range. So, they get reversed from each other. Make sense? Any questions? All right, let's do some. If possible, find the exact value. And frankly, that equivalent equation is exactly where I go with this. Okay. This, folks, is a number, not an angle, remember? So the answer to this is going to be an angle, right? So what you want to name the angle? You get to choose something. Name it. Fred, Pete, Sue, whatever. Say again? All right. I was sort of kidding, kind of, but I like to see things that I know I'm going to remember as an angle. And to me, the favorite is theta. Let's just call, you don't have to use theta. You can use anything you want to. Sue or Pete would be fine, but let's call it theta. Okay? A Greek name. This is a Greek angle. Okay? Now, give me an equivalent equation to that. We want to find theta. That's what we're looking for. Give me an equivalent equation to that. -1/2 is, oh, you use y? That's fine. Is equal to sine of y. Okay, that's fine. I use theta, but you can use y. Okay. Yeah, it doesn't matter. Whatever you want to call it. But the reason I use theta, I think of angles as having the Greek letters and numbers as being the English letters. But if you like y, that's perfectly fine. Now we want to find the angle y whose sine is -1/2. What would that be? Okay. Help me, somebody. Pi/6, that's close. -pi/6, perfect. Okay? -pi/6. Okay? Does that make sense? That's the arc sine. You're looking for the angle. The angle has to be, and since it's negative, and you're restricted to the fourth or first quadrant, sine is positive in the first quadrant, negative in the fourth quadrant, so it must be -pi/6. Okay? What would be an equivalent equation to this one? I want to name this some. This is a number. I need an angle. What angle do you want to name it? Oh, you want theta this time, and now you're going to call it y, right? Okay, give me an equivalent equation to that. An equivalent equation to that. Square root of 3 over 2 is equal to sine theta. Perfect. And what theta would fit that bill? Pi what? Over 3. Okay. Theta equal pi thirds. Positive because you're in the first quadrant. Positive value. Okay? How about C? Give me 2's a number. We're looking for an angle. What do you want to name the angle? Say again? Theta. Okay, let's name the angle theta. Give me an equivalent equation. 2 is equal to sine theta. All right? Give me the angle theta whose sine is 2. Say again? Don't rack it too hard. It's not. There's not one. There is no angle in the world whose sine is theta. Because remember, the sine is always between -1 and 1. No answer. That's why your calculator was given domain error or something like that, right? So this is no answer, okay? No value. Whatever you want to say. It can't happen. There is no angle whose sine is 1. That is 2. None at all. Okay. So, not defined. Whatever you want to call that. What do they say? Not possible. That's perfectly fine too. All right, let's see how the book did it. Okay. Any questions on this before I erase it? Okay. I always write, just about always write, the equivalent equation, and to me those are far easier to mess with. Okay. So on the first one, because sine of I guess this is okay. I mean, we're almost doing the same thing. But they say because the sign of the answer is that, then that's the answer. And that almost is real circular to me. I would write down, name that, whatever you want to name it, and then say the sign of that angle is -1, which is exactly what they're doing here. But they're giving the answer first. And here's the thing I didn't specify, but we did talk about it. We said fourth quadrant. It has to be between negative pi halves and pi halves. It's got to be, okay? And so that is the one that's within that range, okay, that whose sine is -1/2. It does lie in there. So inverse sine of 1/2 has to be -pi/6. Angle whose sine is -1/2. So first thing I do, remind myself, that's the number, we're looking for the angle. Okay. And again, they say because it's true, okay? To me, that's a little circular in logic. But it says you're looking for some angle, theta or y or whatever you want to name it, whose sine is square root of 3 over 2. Well, that would be pi thirds. Okay? And pi thirds, that's why inside that range of domain. Okay? So it follows this because the angle whose sine is the sine of pi thirds is root 3 over 2. All right. Now remember, there's lots of angles whose sine is root 3 over 2. We want the one between -pi halves and pi halves. And there's only one there. And then the third one, it's not possible for that to be true when x equals 2 because there is no angle whose sine is 2. The sine of any angle is between -1 and 1. Can't be 2. Remember, the domain of the inverse sine function is -1 to 1. So it's outside that because it can't have a value of 2. All right, example 2. They get 2 in a row. They say sketch the graph of y is equal to inverse sine or arc sine of x. Now, it's sort of bizarre. They just showed you one just a couple of slides ago, it seems like, but we'll do it. All right. Now, here again, I remind myself, what kind of value is x? A number. And y? An angle. Expressed in what units? Radians. We don't mess around with degrees unless the problem specifies degrees. So we're dealing in radians. Okay? So y is in radians. So your horizontal axis is going to be numbers between what two numbers? No, those are angles. So that's going to be your vertical axis, is between minus pi halves and pi halves. Okay? Because your y is your angle. This is your number. Okay? So what will your x's be? Between what and what? No, those are your angles.
Oh, 1 and 1?
Yeah, negative 1 and 1. Okay? Now, if you draw these to scale, and I usually don't, just remember that pi is just a little bit more than 3. So this would be minus 3 halves to plus 3 halves, approximately. Not exactly. So therefore, those should be a little longer, and these should be a little shorter. I don't usually get them to scale, but if you're trying to draw the scale, that's what you would have. Okay, now where do they begin? When x is minus 1, this is at negative pi halves. When it's 0, it's 0. And when it's 1, it's pi halves. Now, those were the easy ones. Okay? We need a couple more in there too. Okay? Now, I find that minus 1/2 and positive 1/2 are probably the next two easiest. And what are the values, the angles that would produce those numbers? Sort of answered one of these before.
Negative 1/2 would be negative pi over 6.
Yes, the 6 of pi. And since that's a third of pi halves, let's just split this into 3s here. Okay, so this will be here, and this one will be here. I usually don't split. Now remember the other thing, remember, this is almost a vertical slope here. So come up from an almost vertical slope to here, almost linear in there, and then almost vertical slope again. So that's my way of drawing this. Remember, the slope is almost vertical here. You have from here to here is almost linear. And then there on. Okay. And if you think of this see, mine's not quite the scale. Pi 6 is really close, or negative pi 6 is very close to negative 1/2, right? So pi is 3, a little bit more than 3, so 3 over 6 would be 1 negative. Negative 3 over 6 would be very close to negative 1/2. So that's why this is almost linear right here. Almost a straight line. Not quite. Almost. And that should be very close to your identity function. Obviously, my scale isn't correct. Okay, so that's why it doesn't quite look right. But then again, almost vertical slope up there, almost vertical slope here, almost vertical slope there, 1 to 1 in the middle. Yeah, it's pretty easy once you remember those little issues. Okay, that's how we did it. Let's see how they did. They are a lot more extensive with theirs, I'm sure, than what we were. Okay. By definition, the equations y is equal to arc sine x and sine y is equal to x are equivalent for minus pi halves pi halves those values for y. So the x's would be from minus 1 to 1 corresponding to those. So from the interval minus pi halves, you can assign values, and you can put them all in there like they did. Actually, they didn't do pi thirds. They could have. That would be, this is 1/3 of the way, this is halfway, this is 2/3 of the way between those two. That way too. Why they just those two, I don't know. But this is hard to graph. Square root of 2/2. Yeah. 1/2 is easy to graph. Ones are easy to graph. Zeros are easy to graph. Okay. You got your other scale got to be in fractions of pi anyway, so just get those right. This is 0 pi halves. This is 1/3 of the way between 0 pi halves and 1/3 of the way between 0 and negative pi halves. So it's pretty easy to do. I don't know. Minus pi fourths and pi fourths, they don't do a lot for me. So I can live with the other two. Okay? You don't need all those. You can put it more in if you wanted to. Square root of 3/2 doesn't do a lot for me either. Okay. All right, so here's how it looked. I think we came pretty close to it, just doing the way we did. Your vertical slope here, this is almost 1-to-1 here. This is just your x-axis is from -1 to 1. This is 1/2 here, and this is negative 1/2 and negative pi 6, which is awfully close to negative 1/2, a little bit more than negative 1/2. So this is almost a linear function, almost your identity function from minus pi 6 to pi 6, minus 1/2 to 1/2. And then it curves to going back toward a close to vertical tangent line there. Does that make sense? Now, note that there is a reflection of the line y = x of the black portion of this graph. They don't really show that, but they could. Remember that the domain of y is equal to the inverse sine of x, or arc sine of x, is the closed interval -1 to 1, and the range is the closed interval negative pi halves to pi halves. For sure, put that down first. All right. Any questions on that? By the way, every time you see an example in the book, we've just done 2 of them, there is a checkpoint following. Good thing to do sometime before the next class. Actually, as soon as this class is over. So other inverse trigonometric functions, let's start with the cosine. Cosine, we have a little bit of problem. You can't do the same thing we did sine. You can't go negative pi halves to pi halves, because that's not 1-to-1 there. Okay? So you have to choose some other interval. Well, where is cosine 1-to-1? Between 0 and pi. Okay? And that's how it looks. Strictly decreasing, meets all the values, everything works there. You can't do minus pi halves to pi halves, because that's not 1-to-1. So now your interval of interest is 0 to pi. That's for the cosine. What that is going to mean for inverse cosine, that's also going to be a strictly negative function, a decreasing function. But now you flip your coordinates, so your 0 to pi is up here, and -1 to 1 is here. Okay, so you have to. It's a very different looking function. Okay, and to me, it's always harder to draw, so that's why you do it carefully. Okay. Consequently, on that interval, the sine cosine function does have an inverse function called the inverse cosine function, denoted either by arc cosine of x or inverse cosine of x. Either one of those is fine. But remember, its domain and range are different from that of sine inverse sines. Okay. Similarly, you can define. Oh boy. They just skipped right over that. So let's do all right. Let's go back here. And let me, again, here. What's an equivalent equation to that one? Y is equal to arc cosine of x, or inverse cosine of x. What's an equivalent equation? X equal cosine y. Perfect. Okay. Remember that. That's the best thing to remember. Okay. And remember what these are. What are your y's representing here? Those are the angles and the x's of the numbers. Okay. And remember what cosine values they are, and you'll be okay. Okay. So, skipping right on through, not doing any exercises yet, let's just get this. Somewhere you can define an inverse tangent function by restricting the domain y is equal to tangent x to the interval. Okay, you have to restrict the domain to minus pi halves to pi halves. Now, how is that different from sine? It looks pretty similar. It's not quite the same. And there's a reason for it. Sine is a closed interval. Tangent is open interval. Tangent is not defined at negative pi halves or any of your half planes. Sine is, but tangent is not. So be sure that you're dealing with open intervals there. So, except for that, it looks similar. Well, there are some other pretty big differences. Following list summarizes the definition of these three most common inverse trig functions. Technically, sure, you could have an inverse secant and an inverse cosecant and an inverse cotangent, but why would you want to? Inverse cotangents are not terribly bad. The other two are awful. Because if you think about them, they look like this. Okay? So you have to have part of this one and part of that one. These you can't have, okay? So they're not even close to continuous. These three are continuous within those domains. Okay? So that's why we usually only mess with sine, cosine, and tangent to have inverse functions. So this summarizes them. Y is equal to inverse sine of x or arcsine of x, if and only if sine of y is equal to x. That's the thing to remember. To me, that's most important. The domain here of your x, that's the number part, minus 1 to 1. Your angle part, the y, minus pi halves to pi halves. Notice the equal signs are in both of those. All four of those. Okay. Cosine the same way. The only difference is inverse cosine or arc cosine if and only if cosine y is equal to x. Your domain's the same, minus 1 to 1, but the range is different. The y has to be 0 to pi. Remember, that's where cosine's 1 to 1. Sine's 1 to 1, minus pi halves, cosine 0 to pi. Now, the arctangent or the inverse tangent of x, if and only if tangent y is equal to x, that's only defined for angles between minus pi halves and pi halves, not including the endpoints, because it's not defined at the endpoint. So you have to have strict inequalities there. But what are your values there? The x values? Minus infinity, positive infinity. So therefore, now that's what you have for your domain of the inverse tangent, minus infinity to infinity. Okay, where does it start? It starts negative, going toward negative infinity at negative pi halves, and then comes up as 0 at 0, and then goes toward positive infinity, toward positive pi halves as you x goes to positive infinity. So those have horizontal asymptotes at your half pies, just like the vertical asymptotes for tangent at the half pies. All right. So here we have the inverse tangent, inverse trig functions, the big three. Inverse sine, okay? Remember, it's your vertical slope here and a vertical slope here. It's going from negative 1 to 1, or your numerical values, your angle values, which are your y values here, negative pi halves and pi halves. Here it's negative 1 is negative pi halves, 0 is 0, and 1 is positive pi halves. And this is close to one-to-one identity function here, and slope, slope of 1, very close to it there. Okay. Arc cosine, rather bizarre, because your cosine function starts at 1 and goes down to negative 1 at pi. This starts at negative 1 at pi and goes down to 0 at pi halves, just like cosine of pi halves is 0. Inverse cosine of 0 is pi halves, and then it goes down to 1. Again, there are vertical slopes here, so remember that. Your intercept here is pi halves, because cosine of pi halves is 0, so the inverse cosine of 0 has to be pi halves. And then that gets everything where it belongs. Okay? Sine is strictly increasing, cosine is strictly decreasing. Now, this is not going to be quite to scale. I think I'll put it in a different color. What color you want it? Say again? Blue. Light or dark? Dark. Okay. All right. Let's guess out here and make this minus pi halves and make this positive pi halves. I usually don't put them on the same graph, but there's a reason for this. This then will be a minus 1, which would be about here. That'll be a plus 1 about here. Okay? Okay? So let's see if I can do this. The sine function will go something like this. Okay? And I haven't drawn this very well, but here is your identity function here, and you see those reflect across that pretty well. I mean, my drawing stinks, but you got the general idea. Now, a little bit tougher on cosine, okay? So let me go back to dark here, black here. Cosine of 1, let's see. Your 1's going to be about here, and your pi halves is going to be about here, and you're going on this way to pi is going to be somewhere about here. I hope that's right. Okay, cosine starts here, crosses there and goes down here. So there's, ooh, I meant to put that in blue, sorry. Let me erase the black. Okay. Go back to blue. Okay, now that's not exact, but if you picture your one-to-one function, I mean your identity function, it's like this. And sure enough, well, close to it. Again, reflections, but they don't reflect well. These two reflect well, those two reflect well, but you know, there's some place in there where it gets lost. So there's still a reflection. Let's get those off of there, or at least part of them off of there, and let's look at tangent. Okay. So tangent, ooh, let me get my black back. Okay. That's going to be approximately pi halves, and this is going to be approximately minus pi halves. Okay. Now, for your tangent function, these are vertical asymptotes. Okay. And go back to blue again. At pi fourths, which would be about here, you're at minus 1, and at positive pi fourths, you're at plus 1. Okay, so this function does sort of like this. Okay, and again, a very good reflection across your identity function. Okay, got lots of red on there, but you see, whereas this goes to infinity here, goes to infinity there, this is going, your x is going to infinity there, and x is going to infinity there, staying between what were your vertical asymptotes you can't possibly touch, now they're your horizontal asymptotes that you'll never touch. You approach them but don't get there. So they sort of truncated that a lot, but it goes on forever. And that is something that they probably should have drawn a little bit more there. That's not truncated like these two are. It goes on forever. Okay. Limits there, but not otherwise. Does that make sense? Okay. A lot of ugly drawing, but hopefully. All right. So let's now do example 3. Find the exact value. That doesn't mean approximate on your calculators, okay? So what is the equivalent expression of this? First, what are we looking for here? A number and an angle. An angle, okay? What you want to name it? Say again? Theta? Okay. I like theta too. Give me an equivalent equation to that one then. Somebody help me. The square root of 2 over 2 is equal to cosine of theta. Is that what you said? Okay. Well, angle theta is going to fulfill that requirement. Theta is equal to pi fourths. And that is between 0 and pi, so yeah, that's good. Okay? How about the next one? What are we looking for here? An angle? What you want to name it? Oh, I got you convinced, huh? What is that equivalent to then? Zero is equal to tangent theta. And what angle will that be equal to? Pi half theta is not defined. Vertical asymptote point over there. Zero. Because theta is equal to theta. That's pretty impressive. Okay. Theta is equal to 0. All right. Because sine is 0 at 0, and theta and tangent is sine over cosine, so it has to be 0. Okay? How about this one? What are we looking for here? An angle. What name you want to give it? Theta again. Y'all got you convinced, huh? What's an equivalent equation to expression to that equation? -1 is equal to tangent theta. What theta would fulfill that? Negative pi over 4. Negative pi fourths, right? Because that's your 45, okay? That is where sine and cosine are equal. So except it's negative. So it's the negative pi fourths. Okay? Make sense? All right. If you remember the way you graph, remember that was that key point. I said the book never mentioned them that much, so they usually put them in there. That's where your A fits into your tangent theta. If that was A tangent theta, your A value would be either minus A, at pi fourths, at your quarter pi's it would be either plus or minus A. So let's see how they did it, because and again, they give the answer, because cosine of pi fourths is root 2 over 2, then pi fourths lies within that, it follows that the arc cosine of root 2 over 2 is pi fourths, which to me just seems awfully circular, okay? And it is. And because tangent of 0 is equal to 0, 0 lies in between minus pi halves and pi halves, it follows that arctangent of 0 is 0. And because tangent of minus pi fourths is minus 1, negative pi fourths is within minus pi halves and pi halves, then inverse tangent of minus 1 is minus pi fourths. So again, it just seems awfully circular the way they try to explain it. I like to go and put an angle in there and then find the angle, which is what they're doing, but they're just doing it right up front without any clarity, I think. But anyway, maybe not. All right, so that was example 3. I'm trying to find where that slide is. By definition, something we've already said. Okay, yeah, it's at the bottom of the page. Let's do example 4 first. All right, let's do it here. Use a calculator to approximate the value of each expression if possible. First one of these is arctangent, which is the same as inverse tangent of negative 8.45. Okay? Now, it seems like a pretty big number. Is that possible? No? Remember, okay, let's think in terms of tangent now. Tangent is restricted between vertical asymptote minus pi halves and pi halves, but it takes on any value there from negative infinity to positive infinity. That's the range of tangent. So when you flip it over to make the inverse function, arctangent, now your domain is all real numbers. So negative 8.45, no matter how big it is, that's fine. That's within the domain, but your range is going to be between minus pi halves and pi halves. Okay? So we need the range there. We need the answer there. And your calculators will do this. Okay? Now, be sure you're in what mode? Radian mode. Okay? Be sure you're in radian mode and then do it. And what do you get? I guarantee you it's going to be a negative angle. Okay. Negative 1 point what? 45. Okay. Now, does that seem reasonable? Well, it's a pretty good sized angle. Okay. It has to be between minus pi halves and pi halves, right? Well, minus pi halves is something around minus 1.5. Actually, a little bit greater or less than that. So, yeah, that is within the range. So, yeah, that sounds like a reasonable answer. Negative 1.45. Let's see what the book got. Negative 1.545, 30010. Yeah, right. Who needs that much? Okay. How about this one? B part, if I can get my pen back, there we go, is inverse sine of 0.2447. Oh, they don't put parentheses. Okay, so I'll take that off. Since they don't seem to think it's necessary, I won't either. Now, your function will do it. What kind of value do you expect this to be? Positive, negative? Positive, because inverse sine, remember, it, like that. So, yeah, positive value. About what value n. This is pretty close to 0. There is almost the identity function. So the value is not going to be far off from that. What you get it to be? 0.25. Pretty close, wouldn't you say? They get 0.2472, which is even closer to that. Okay? And then this one. Arc cosine 2c's of 2. Second? Does not exist. D-N-E. Okay, does not exist. That's fine. Only problem with that, I've actually graded papers before, and someone's written it almost that sloppily, and I thought they wrote the number 1. I said, how did they get 1 out of it? That's the detail. So anyway, so does not exist. Error message, don't you get? There is a checkpoint there. Be sure you do the checkpoints. All right, now let's move. Oh yeah. By definition, this was the last sentence after the checkpoint on that page, 321. By definition, the values of inverse trigonometric functions are always in radians. Okay? They don't mess around with degrees here. So, next thing we're going to do is compositions. They say here of functions, the book says of inverse trigonometric functions. Okay? Now, just a little bit of reminder here. Okay. We know that for all x's in the domains of any function and its inverse, the inverse functions have this property. If you have a function as an inverse, and they do and everything fits, f of alpha inverse has to be x. No way around it. Okay? And f inverse of f of x has to be x. Whatever you input here with the inverse function, that output, say, is a y, okay? And because this is the inverse function of that, if you take the f of the y, you've got to get x because you're exchanging your values, okay, your coordinates. Same thing here. If your x is your input here, your output's going to be a y, and f inverse of y has to give you that same x, so you wind up with the same x you had to start with. An inverse function undoes a function, and the function undoes its inverse. So whatever the input here is, that's going to be the output once you do the inverse of it, okay? Got to be. Now, so here are the inverse properties of trig functions, okay? Now remember, generally in algebraic functions, they're either going to be strictly increasing or decreasing everywhere, or else you fix domains. Here, you've got to have fixed domains, and ranges too, by the way. Okay? And this is, remember, your arc sine, this is your number, okay? And your answer is going to be your angle. So the numbers are from -1 to 1. The x's are from -1 to 1, and then your y's are from -pi halves to pi halves, even though you don't see a y on the page until you're over here. Okay? Well, here, the sine of the inverse sine is x, but that's only an x between -1 and 1, because you can't take an arc sine of anything outside of that. But if you're doing this way, the arc sine of sine y, here is the angle. Okay? This is going to be the number, and then the arc sine of the number is going to give you an angle. These angles are now restricted to -pi halves to pi halves. So it looks the same, whichever one you put inside or outside, the inverse or function inside or outside. But this shows up here, this shows up there. But remember, the values for these are this, and the values for that is that. So, beating it to death. Here, same x values here for inverse cosine, okay? That you can take an inverse of those numbers. Now your y's are between 0 and pi, because your cosine of y expands the range from 1 to -1. So it has to be same statements here are true, but they cover different ranges of domains. Now, here for tangent, for x being any real number, remember, because the tangent of any angle can go from minus infinity to positive infinity, all real numbers as a range, that becomes all real numbers is your domain of your inverse tangent. Okay? But if you do the tangent first, then that has to be between minus pi halves and pi halves. Between them, not including like sine, but between them. Not including the values because they're not defined at those half times. Tangent is. Okay. So with that in mind, we can do these things that we're required to do. Those inverse properties do not apply for arbitrary values of x and y. Okay? Now, you can certainly take the sine of 3 halves pi, right? No problem there. Sine has a domain of all real numbers. Within the arc sine of the sine of 3 halves pi, it'd be 3 halves pi. No. Because the output of an arc sine has to be between minus pi halves and pi halves. Remember, the range of that is minus pi halves and pi halves. So the sine of 3 halves pi is minus 1. And you do arc sine of minus 1, though, your calculator is going to tell you minus pi halves, not 3 halves pi. Now, if you draw those on a unit circle, you're at the same place. 3 halves pi is over here, and minus pi halves is here. You're at the same place on a unit circle, or on any circle, really. But you can't express it this way. Okay? You have to be within the range of arc sine. And the range of arc sine is only between minus pi halves and pi halves. So in other words, this property here that was on the previous page only applies when the y is between minus pi halves and pi halves. Remember, they said that before, but there it is not valid for values outside that interval. So this property is true as long as you're inside this. If you're outside that, this is still true, but it's not that answer. It's this answer, okay? So they're not going to be the same values there if that y is outside. Okay. Does that kind of make sense? It's because you have that limit there. Thought I had this out, but I don't. All right. Let's do something. If possible, find the exact value. Okay? The tangent of the arctangent of -5. You think you can do that? With a calculator, you can do anything, right? Okay. What do you think here? What? Let's start on the innermost thing. What are we looking for? What does this -5 represent? A number. So this thing represents an angle, right? Okay. Now, is there an angle whose tangent is -5? Remember tangent? It goes to positive and negative infinity. And -5 certainly down here somewhere. So yeah, there is an angle. It's awfully close to minus 3 pi halves, but it's not. You know, it can't be that. So yes, you can. And then if you take the tangent of that angle, you're going to get -5. So that one works. That one works quite nicely. -5. Going to be it. That's within the domains and ranges of everything. Okay, how about that one? Can you take the sine of 5 pi thirds? Okay. I like to think where we are, Waldo. There's 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi, 5/3 pi. Yeah, we're down here somewhere. What you reckon value that is? Negative, I think that's more like the sign of that is the y value, √3/2. Okay? That's what its value is going to be. Now, if you did the arc sine of √3/2, where you reckon you are? Okay, not quite. You see, you can't have it. Oh, yes. Negative pi-thirds, you're right. That will not be the same value there. It will be the same location on the circle. That's why I draw it that way, so I can see what it is. But you see, the inverse sign is only defined from minus pi halves to pi halves, not defined over here. Okay? So negative pi-thirds. Okay, how about this one? The cosine of the inverse cosine of pi. Say again? Did I hear a pi? I love pi. Never mind, that's a dumb joke. Okay. What you think? Cosine of pi is 1, that's correct. How about inverse cosine of pi? Actually, cosine of pi is not 1, it's minus 1. Right? Okay. That's beside the point. How about the inverse cosine of pi? Okay. What are we looking for? Inverse cosine is going to give us an angle. So we want an angle whose cosine is pi. So we want cosine of some angle theta is equal to pi. And what you think? Pi is about what? Approximately? 3.1416, blah, 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 blah. Okay. Guess what? Cosine is between? Oh, no, 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 no. Can't do that. That's your good old D and E, right? You cannot take the inverse cosine of pi because it's outside the domain of cosine. Okay? Cosine is only between, wait, I'm sorry, yeah. Outside the range of cosine, the domain of inverse cosine has to be between minus 1 and 1. Pi is outside that. So that one doesn't exist. So let's erase my ugliness here, or some of it anyway. And what do we have here? Yeah, because negative 5 is in the domain of the inverse tangent function, the inverse property does apply, so you can just write it down, okay? But in this case, 5/3 pi does not lie in there. The arcsine function is only defined for minus pi halves to pi halves, and the angle that's in there that's equivalent to 5/3 pi is going to be your negative pi-thirds, okay? So that is the answer of that one, negative pi-thirds. And in the other one, that expression is not defined because inverse cosine of pi does not exist. They're outside the range, domain of inverse cosine. Domain of inverse cosine is negative 1 to 1. Pi is way, way, way outside that. Whoa, last slide, but we're not through. What's that? Okay. Are we almost out of time? Very close. We'll begin next time with example 6. There is a checkpoint at the bottom of page 322, so we're going to hopefully finish this next time. Example 6 and 7. Let me erase the one at 7 because we're not there yet. Okay. Homework exercises here include any of the odds 5 through 17. They're all at Calc Chat. 5's at Calc View. Do 19 is the Calc Chat. Any of the odds 21 to 35, they're all at Calc Chat. 21's a Calc View. Do 37, it's a Calc Chat. Any of the odds 39 to 43, they're all at Calc Chat. 39's a Calc View. Any of the odds 45 to 49, they're all at Calc Chat. 45's a Calc View. Any of the odds, okay, let's see. Yeah, you can start working. Wait a minute. Start working on the odds, yeah, 51 to 61, they're all at Calc Chat. 55's a Calc View. We'll pick up the rest of those next time. Good deal. We'll get out of 4-7 finally.